Our next speaker is a faculty member at King's College London with interests in the societal impacts from climate change with a focus on severe weather. From deadly tropical heat waves to severe cold weather mountain windstorms, his research aims to map the limits of Earth's climate envelope and chart its course as it's shifted from as it's changed with human-caused climate change. As part of the Rolex and National Geographic Perpetual Planet Everest and Amazon expeditions, he scaled the highest peaks in the Himalayas and the Andes to collect critical climate data in these high-altitude environments. Here to talk about the planet's most extreme climates, please welcome Tom Matthews.
Thank you. Okay, good morning, everyone. So, humans have an ability that is remarkable in the animal kingdom. We have a superpower. And clearly, I'm not referring to extraordinary strength or phenomenal speed, and not even our unusual, perhaps unusual brain power. No, I'm referring to the fact that humans are incredibly sweaty. We are perhaps the most prolific sweaters in the animal kingdom. We use this sweating to help keep us cool. The evaporation of sweat consumes energy. That energy comes from our skin, and it lowers the temperature of our skin. We've all felt the benefits, or rather the cooling effect of evaporation, other than through sweating, when perhaps we get out the swimming pool or get out the sea after a swim on a typically marginal British day in the summer when it's not quite warm enough to go in the water. You're wet, the wind blows, that chill you feel is coming from the water evaporating from your skin. And we use that evaporation to keep cool when we sweat. Now, sweating might seem like a relatively innocuous adaptation, but it has perhaps some deep impacts, or rather, it's a key part of the human story. It may, for example, help explain why we stand upright and lack body hair, so different from the other primates. You see, our sweat-based cooling system works best when we're standing upright and exposed to the wind. It also works better, the evaporation proceeds more easily, when we don't have body hair covering our skin. So our position or our stature as a naked, upright ape might be linked to this importance of sweating in our evolution. And certainly our early ancestors needed every cooling trick in the book as we moved out onto the savannah, into the heat. It gave us a survival advantage, being able to move during the hottest parts of the day, hunting and foraging. So being able to keep cool, particularly by sweating, is our superpower. And it may also play an important role, or is an important part of the story, as to how we became the global species that we are. Our heat coping mechanisms evolved in the tropics and subtropics, the hottest parts of the planet. That meant that no part of the Earth's surface was too hot for us. We could go anywhere. And of course, we borrowed the furs of other animals to protect us from the cold. So our role or our ability, our status as a global species, perhaps is also linked to this ability to fight the heat. So in the context of the unprecedented warming that we're seeing as a consequence of greenhouse gas emissions, what does this mean for the planet's most heat-adapted species? Should we be concerned in the context of these physiological adaptations? I would say, yes, we should be, very much so. And that's why today is really a call to action, to point out exactly what the challenge is and how profound it is. So this is perhaps not unfamiliar to you. We already know that heat kills. As recently as the summer of 2022, when the UK broke its high temperature record, we saw over 60,000 deaths in Europe associated with the extreme heat. And for reference, that's about the same number as were killed in England and Wales from COVID during 2020 at the peak of the COVID pandemic. This wasn't an exception either. In 2010, 50,000 were killed in Russia from a heat wave there, and in 2003, back in Europe, 70,000 deaths. So we already know heat is a killer. What's causing the deaths during these heat waves? It isn't heat stroke, typically. It's cardiovascular disease, as the body is straining to keep cool. The heart is working harder, it's pumping harder. And anyone with cardiovascular disease is at a greater risk of mortality. If you're young and healthy, well, let's just say if you're healthy, you should be able to keep safe in the heat waves that we've seen. By minimizing activity, drinking water, staying out of the sun, you should be able to keep safe. But that might not be true of the heat waves of the future. My concern is that the deaths that we've seen, the impact from heat that we've seen, is very much just a tip of the iceberg. And let me explain why. The body, even when at rest, is generating metabolic heat, pumping the heart, digesting food, regenerating heat. A resting human, about 80 watts, which is about the same as released by a typical burning candle. So you can think of this burning candle within us when we're stationary or at rest, producing 80 watts of heat. Now, in order for our body temperature to not rise dangerously, we have to dissipate that heat. And we're normally doing this all the time, naturally. About 80 watts when at rest. If we start to exercise, we have to dissipate more than 80 watts in order to stop our core temperature from rising. And we do that via this remarkable subconscious choreography. If we need to lose a bit more heat, more blood is pumped to the skin. That's why we flush red. We can also turn on sweating and increase the rate of sweating to cool us down. We never notice this is going on, but our core temperature remains at about 37 degrees because of these autonomous adaptations or responses from the body to dissipate heat. But they do have a limit. So even when the cooling mechanisms are turned up to the maximum, or rather when they are turned up to the maximum, it might be that we can't dissipate heat. And then that heat would be accumulated and our core temperature would rise. Once it gets to about 42 degrees, we should expect heat stroke and, unfortunately, death. And to give you an analogy, we all know that the car engine stays cool by the fan blowing air across the engine. But what would happen if the air was warmer than the engine? It doesn't matter how fast you blow air across that engine, you're not going to cool it down, you're going to heat it up. The same thing is true for the body with our taps turned up to the maximum and trying to cool. If the air is too hot and humid, we cannot dissipate heat and it just accumulates and our core temperature rises. So what is the limit for humans? How hot can we tolerate? What's the maximum temperature? Well, it depends on the humidity. At low relative humidity, that's the vertical axis, sweat-based cooling works better, so we can tolerate higher air temperatures. For example, relative humidity below about 20%, we can tolerate temperatures above 50 degrees. As the relative humidity climbs, it's up to about 80%, can only tolerate temperatures in the low 30s. So how close do we come to this limit? How close have we come in the heat waves of the past, these deadly heat waves? That is the UK temperature record and the humidity during that temperature record. Now, on that slide I showed from the 2022 heat wave, the UK was one of the bars that was there. We saw several thousand excess deaths, just short of 5,000. In theory, that heat wave was very much within our physiological limits. But how close do we get in the rest of the world, in the hottest and most humid places on Earth? I'm now going to share with you the results of surveying 500 billion temperature and humidity combinations. And we're going to pull out the conditions during the hour for every part of the Earth's surface that we got closest to that line. We're going to see what it looks like. So we're going to mark the temperature and humidity combinations during the hour that we got closest to that line. And there's going to be lots of points. So rather than plotting the points individually, we're going to color in that space. Lighter colors will mean more frequent temperature and humidity combinations. Darker colors, less frequent. White, not observed. That's where we've come. It's no coincidence that we are hugging that red line. Very, very rarely in the hottest parts of the Earth's surface, we have crept across that line. It's the bottom right of the plot for the briefest of periods. It's no coincidence that our limit, that red line, pretty much marks the outer envelope of the heat and humidity that has been observed on Earth. In other words, we have evolved, our physiology has evolved to cope with the most extreme heat and humidity the planet can throw at us. But what about the future? We are warming at an alarming rate. Radiative forcing that we're experiencing is perhaps unprecedented in hundreds of millions of years. This is what we'd expect at 1.5 degrees of warming. More regions start to creep over that line. The likes of Lagos, Karachi, Shanghai start to experience heat waves exceeding that limit. At 2 degrees, those places breach that threshold more often and new places cross the limit. Karachi, 10 times more often, or 20 times more often. Lagos, 10 times more often. If we get to 4 degrees of warming, and by the way, 2 degrees of warming is that upper Paris limit. 1.5 degrees, that's what we hope to limit warming to, that's the lower Paris limit. 4 degrees, this is thankfully now unlikely, but would be possible or likely if we carry on emitting greenhouse gases without mitigation. That's a 4-degree scenario. We sail a long way into the unknown. Large parts of the tropics and subtropics would experience heat waves beyond our physiological limits. If we get to 8 degrees of warming, this is possible but unlikely. Possible if we trigger dangerous positive feedbacks. Then a large fraction of the Earth's surface would be too hot for our physiology. Our bodies, even though we are the supreme species when it comes to dealing with the heat, a large part of the Earth's surface would not be habitable for us. So what can we do? There are 2 messages that come out from that slide. Let me go back so I don't distract you with that image. There are two messages that come out from that sequence. One, this is a very compelling reason to limit warming as much as we can. A very compelling reason to reach net zero as soon as possible, to limit the extent to which we sail into the unknown. But there's another message that comes out. Even at 1.5 degrees of warming, major megacity regions cross that threshold. More so at 2 degrees. So even if we're successful with limiting warming, successful with our mitigation, we are going to test our bodies like never before from the heat. So what can we do? Well, air conditioning is the one thing we know works. When it's too hot outside, we know we can turn on the air conditioning, we can provide these cool refugia. But if air conditioning is going to be part of the solution, we're going to scale it up. It needs to be done whilst being powered by renewable energy sources. Otherwise, we're in trouble in terms of meeting that net zero pledge. It also has to be delivered, the power has to be delivered by resilient energy infrastructure. We cannot afford to have the power going out during these heat waves. The infrastructure must be able to withstand the surges from power demand that comes from everyone turning on their air conditioning. It must also be able to withstand the more extreme the other types of extreme weather we expect, be it from hurricanes or floods. For example, Hurricane Maria, Puerto Rico knocked out the power for months. We cannot afford to have that when threatened by such heat waves. We might also want to be thinking outside the box. How can we keep safe even if the power goes out? Building heat shelters that are similar in some ways to storm shelters that can provide us with that cool refuge even without air conditioning. Continuing to improve our monitoring and our forecasting to give people early warning of this specific threat. It's a heat wave that's different from a heat wave you've seen before. Just keeping still and drinking water and using a fan is not enough. You will overheat. It's a different threat. Forecasting will need to evolve to communicate that threat. And let's not forget the lessons of the past either. Indigenous knowledge about how to build cool homes that do not require energy to keep cool. Because this problem is growing fastest in Asia, South Asia in particular, and in sub-Saharan Africa. These are places where the population is still growing rapidly, and there is going to be lots of construction in the decades ahead. Lagos, for example, you heard me talk about Lagos, a place that will start to see such heat waves, 1.5 and 2 degrees of warming. The population there might grow to 60 million people by the end of this century. There is a lot of construction ahead. We must make sure it's done with beating the heat in mind. But I do have some hope with this, because humans do have another superpower: teamwork. The planet has warmed already by about 1 degree in the last 100 years. But we are 50 times less likely to die from a natural disaster than we were in 1920. Why? Because we built infrastructure that's resilient to natural disasters. We built forecasting systems that warn us that disasters are incoming. We've done that by working together at enormous scale. And we must continue to do the same. That ability to work together has brought us to this point where we know the threats that lurk, and the threats in particular from extreme weather, the context of what I'm talking to you about, but extreme heat, a different type of threat that lurks. We still have the opportunity to shape the future. How much warming and our drive to net zero, but also how well we face the hazards that come with the warning. So this is the call to action. We must do better at dealing with the heat waves that are so far unseen. So I'll leave it there. Thank you.